In this video, we discuss continuity and one-sided limits. As you've seen already, we've kind of handled one-sided limits. It doesn't show up in the textbook until this section. So I'll hit on it a little bit here, but for the most part, it's something that we already kind of have a good grasp on. The main idea here will be about continuity. So informally, what we talk about as continuity, a continuous function, we'd say is a function that we can sketch without picking up our pencil, right? So in general, there's no holes, gaps, jumps, etc. Right? There's nothing kind of causing any problems. We can just draw the function, and we know many of these, right? We know a lot of functions that are continuous, and in fact, they're continuous everywhere. We know a lot of functions that aren't. So what I want to try to do is kind of sketch a couple situations where maybe things aren't so nice. The first would be something that has maybe a hole, and in this case, at x equals c, f of c is just not defined, right? There's nothing there. There's a hole. So we would say that f is not continuous at c. Another example is, say, there's a jump or a gap. Here, we would say that the limit as x approaches c just does not exist, right? Even though the function is defined, the limit doesn't exist there. Okay, so that's not a continuous function. The next would be something maybe where I have a limit, but the function is defined elsewhere when x is c. So this is a situation, where the two kind of first criteria are met, but the third is broken, and that third is that the limit and the function value are the same. So in this case, the function and the limit do not match up, right? So where the function is behaving is not the same as where the function's defined. So this is also not a continuous function, right? I have to pick up my pencil in order to draw it, okay? So this is a three kind of general scenarios where where a function might not be continuous. I'm going to describe the definition for us here, and then I want to kind of go through some different scenarios and examples of how that definition works the way it does. So here is continuity at a point. Okay, so at some specific value c, we say the following. A function is continuous at x equals c when the following conditions are met. Okay, and those conditions are as follows. Number one, f of c is defined. Okay, so that's kind of like the first picture I drew. I'm able to plug in c to my function and get a value back. Number two, the limit as x approaches c exists. Okay, now this second criteria is where we incorporate kind of our left and right-sided limits. We can always break apart a limit into the limit from the left and the limit from the right. And in order for a limit to exist, right, kind of that overall limit, we have to have both the limit from the left and from the right match up, and they have to be the same value. Okay, so that's where we'll use those left and right-sided limits. The third criteria, number three, is that the limit and the function value have to be the same. Okay, and that guy is really what describes continuity, altogether. All right, that third criteria really kind of encompasses the first two. You can't have a limit and a function value match if the limit doesn't exist or the function's not defined, right? So that number three is really kind of what encompasses continuity at a point. I just like kind of dividing it up into these three criteria. Okay. We say that f is continuous on an open interval, a to b, if the function is continuous at each point in that interval. Okay, so I could test all those points, every little point in the interval, and I could then say, hey, the function's continuous on that open interval. Okay, I can say that a function is continuous everywhere if it's continuous at every point on the real line. And on the real number line then is from minus infinity to infinity. These two situations are kind of where we hope to be. In fact, the last one there, continuous on the entire real line, is kind of an ideal situation. We've got a function with no breaks, jumps, gaps, anything for any x value from minus infinity to infinity. Okay? Checking every single value is impossible, right? In fact, it's much easier to find discontinuities, right? So that's where our main focus will be, is to find where functions are not continuous. Where would I have, some function that's undefined, or where the limit and the function value don't match up. That's what our main goal is. So what I want to do here is kind of talk about those three situations again, and kind of what goes wrong, right? So when f of c is undefined here, even though the limit as x approaches c exists, right, from the left and from the right, those match up, I have a function value, the first criteria is broken here because the function is undefined, right? We're going to have a not continuous function or a non-continuous function at c because the first criteria is broken there. In the second middle picture, we have that the limit doesn't exist, right? So as x approaches c from the left, I have a value. As x approaches c from the right, I have a value, but those don't match up. So the overall limit does not exist, and even though the function is defined, even though f exists, the second criteria is broken here. And lastly, even though I have a limit, and I have a function value, the third criteria is broken because those two values are not equal. Okay? So these discontinuities are actually going to fall into two separate categories, and those are removable and non-removable discontinuities. Okay? This one in the middle is what we would refer to as a non-removable discontinuity, right? And the idea is that I can't in any way, rewrite the function or do anything to make the limit, exist there. I can't just kind of make that happen. But the other two we would refer to as removable discontinuities. I can take that discontinuity away by redefining the function or defining a different function that has a function value where it's supposed to be. Okay? So basically the idea is that we can refill potholes, right? We can fix those. We can put asphalt back in, but we can't reconnect jumps, right? We can't just basically close up a fissure, but we can fill in potholes. So I want to do an example where I kind of look at that. Well, first, let's take f of x is 1 over x. With this guy, there's not going to be much I can do. Let's look at the three criteria of continuity. Of course, the interesting place is when x is 0. F of 0 is just undefined, right? There's nothing I can do. I can't plug in 0 there. This is a broken criteria, okay? And right away we can say that the function is not continuous at 0, but I want to see if there's any chance that I can remove that discontinuity. Number 2, the limit as x approaches 0 of 1 over x. This is something we've looked at before, and I want to again here, and this is one of those limits that we broke up from the left and from the right. From the left, we're able to say that limit, that function there approaches minus infinity from the left side of 0. From the right, the function approaches positive infinity. Those two together tell me that the limit does not exist. We've got a number 2 criteria that's broken here. So if I've got a function that's not defined at c, at 0, and a limit that doesn't exist at 0, well then there's no way those two things are going to match other than the fact that they're both broken. Number 3, it's just broken. This function is not continuous at 0. There's absolutely nothing that's going to change that. there's no way we can remove or redefine the function in a way that removes the discontinuity at 0. Okay? F here is just not continuous at 0. This discontinuity is non-removable. Okay? And we could have kind of gathered that before, right? Without knowing the definition of continuity, we could have said a lot about this function at x equals 0. It's just there's nothing there, and there's no way to rewrite this in a way that I can make something be there. Let's look at another example. Here's sine of x, y equals sine of x. This function is rather nice. These criteria are going to seem a little goofy. The function value at c is just plugging in c, right? There's no obvious issues but with plugging in any value, right? I'm not testing any point in particular because I can't think of any good ones to test, right? For all of these criteria, sine of x passes really with, passes with ease. Sine is continuous on the entire real line. There's no values of x that when I plug in are going to give me any issues with sine of x. So that's going to pass every single criteria at every single point on the real line. Okay? Where things get interesting is an example like this. X squared minus 1 divided by x plus 1. Okay? This is a function similar to ones that we've explored while talking about limits. And I want to go through the criteria for continuity here. Of course, when x is minus 1 is the interesting x value. So right here, number 1, f of minus 1 is undefined right away. That's a broken criteria. So continuity is broken right away with the first criteria. So f is not continuous at -1. Okay, but let's see if there's anything that we can do by looking at these other criteria. When I take a limit here, as x approaches -1 of my function, I can evaluate that limit by factoring and seeing that the x plus 1s, what's going to be causing my problem, cancel out, and my limit then I can say is -2. Okay, so my function near -1, when x is -1, is behaving like -2. Right? So my function is approaching -2. And of course, then, f is not continuous. The third criteria is broken because the first criteria is broken. F is not continuous at -1 because 1 is broken. Maybe we can do something. Maybe we can remedy the situation by redefining a function that is continuous at -1 by kind of filling in that hole. So let's say that we're going to require that the function at -1 should be the same as the limit. So what that means is that f of -1 has to be equal to -2. I need the function to exist at -1, and it should have the same value as the limit. So what we do is we redefine the function as something else, call it g of x, and when x is not -1, we know that we just have the original function, right? That's the situation we're already in. But when x is -1, I want the function to have a value of -2. This discontinuity is removable because we can redefine or define a new function in such a way that is exactly the same as the old function. However, when I plug in where things were going bad at -1, I can rewrite the function in a way that I have the same limit as I do function value where the discontinuity was. So this is why we classify this type of discontinuity as removable. I can take it away, right? Again, try to remember that the original function, f of x, it's not continuous at -1. That's it. That's all there is to it. But just the type of discontinuity that we're working with is referred to as removable. Okay? Let's look at a different example here. This function, square root of 4 minus x squared, is a little specific, and I want to talk about a certain concept here involving continuity and one-sided limits. This is an interesting function. I want to try to look at the domain of this function, right? Where is this function, where does it exist? So for that, I need the inside here, 4 minus x squared, to be positive or 0, right? I can't take the square root of negative numbers. So what I'm going to do is try to dissect that a little bit. Under factor here, this means that 2 minus x times 2 plus x has to be greater than or equal to 0. So if I try to put all this on a number line here, and to figure out where this function is indeed, or where this quadratic, 4 minus x squared, is positive, I'm going to test some values. If I test negative 3 squared is 9, 4 minus 9 would be negative, and that's no good. I can't have a negative under my radical. My function is undefined for anything less than negative 2. Okay? The same thing can be said for anything greater than positive 2, right? I would test the same type of value, 3 out there. 4 minus 3 squared is negative, and under the radical, that's no good. My function's undefined for anything to the right of 2. But in between negative 2 and 2, if I plug in anything in that little interval, 4 minus 0, for example, is 4. That's positive. Everything's good. My function's positive there. So I've determined then that f is only defined on the closed interval from minus 2 to 2. Okay? So we can then kind of assume that f is continuous on the open interval from minus 2 to 2. And I want to know, what about when we close in those endpoints? And the reason I ask is because try to remember the definition of continuity. The function value and the limit have to exist. I can't take an overall limit at an endpoint because I need the limit from both sides, right? I need a left and right side limit. So we're in an interesting situation here. Because of that, the definition of a limit and the definition of continuity, by the way things are right now, I can't say that the function is continuous at those endpoints because the limit, the overall limit, would not exist. But the way that we are able to talk about continuity, we can use the left and right-sided limits in situations like these. We say the limit as x goes to minus 2 from the left is nonsense, right? Because negative 2 from the left, my function is not defined there. My function is not defined to the left of negative 2. However, we can say that the limit as x approaches negative 2 from the right, that's just 0 because I can plug in negative 2. I can approach negative 2 from the right side. My function is defined there. And in fact, what we're able to say is that that's enough for continuity. So even though that the limit as x approaches negative 2 of my function does not exist, we can still say that f is continuous on the closed interval. Okay, so it's enough to have this right-sided limit here for my function that's not defined on the left side of negative 2. By definition, we don't have to do anything extra. It's not that it violates the definition of continuity. It's just we need a way to be able to talk about functions that aren't defined on either side, or maybe not on both sides of a specific value, of a specific x. And in this case, in cases like this, we can say that the function is continuous. So we say that the limit as x goes to 2 from the left, now I'm at positive 2 from the left side, is also 0. So that's enough to say that on the right side of my interval, as x goes to 2, positive 2, I can close things off and I can say that my function is continuous there as well. So this is just a little bit of an aside where I'm kind of zooming in onto left and right-sided limits, but I can also talk about continuity in those contexts as well. Okay? So just try to remember that even though a function might not be defined on one side of an x value, we can still say it's continuous at that endpoint, as long as I can kind of plug in that endpoint. Okay. I want to bring about the properties of continuity here, and these are kind of going to extend from our properties of limits. We're not going to see anything too drastically different from what we're used to here. So let me lay down the ground rules here. If f and g are continuous at x equals c, then the following functions are continuous. Okay, number one, b times f, a scalar function here, or a scalar times our function, our continuous function, is also going to be continuous, right? We know that we can move a scalar out of a limit, so there's really nothing that's getting in the way of that function being continuous. Number two, the sum or difference of two continuous functions is also continuous. Okay. Number three, the product of two continuous functions is continuous. And four, the quotient of two continuous functions is continuous as long as you're not dividing by zero. Okay. So all of these are continuous. And in fact, that leads us to what we can say about specific classes of functions. This implies that polynomials, rationals, radicals, trig functions, and finally exponentials and logs are all continuous. All of these functions are continuous on their domains. And that's the important bit here, is they have to be continuous on their domains. Of course, there are radical functions and trig functions that aren't continuous at some points. But points that exist, that lie in their domains, these functions are always continuous. And that follows directly from these properties. I want to do one more example here where I explore a piecewise function. This is where really things kind of get interesting, is when we talk about piecewise functions, because they are defined one way on one side of an x value and a different way on another side of an x value. Right? We can make them as complicated or as simple as we can come up with. But I've got here a function that's defined to the left side of 2, in fact even at 2, as 1/2 x plus 1. And on the right side of 2, non-inclusive, I have 3 minus x. So it's linear on both sides of 2. And I can say that because of that the function is continuous on either side of 2, but the trouble is exactly at 2. Okay? And the reason that's trouble is because I don't know if the limit and the function match up on either side of 2, right when I zoom into 2, I don't know if the functions are matching in a way that makes so I don't have to pick up my pencil when I'm sketching this piecewise function. So we go through the 3 criteria. Number 1, does the function exist at 2? Well, yeah, because as x is less than or equal to 2, that implies that I can have x be 2. So when x is 2, I'm going to use the top half of my piecewise function and say that when x is 2, my function has a value of 2, right? 1/2 times 2 is 1 plus 1 is 2. The second criteria is that the limit as x approaches 2 has to exist. Now for this, I have to look, remember the function or the limit doesn't care about the function value. So I have to look from the left and from the right to determine the value of this limit. Okay, on the left side of 2, my x values are less than 2. So I'm going to use the top half of my piecewise function again and look at the limit as x approaches 2 from the left of minus 1/2 x plus 1. I can evaluate this limit with direct substitution. I should get a value of 2. Okay, just like I did the function value, on the left side of 2, things are good, things make sense. The function's the same as the limit. But here's where things get interesting. On the right side of 2, my x's are bigger than 2. And since x's are bigger than 2, I'm going to use the bottom half of my piecewise function. I need to evaluate the limit as x goes to 2 of 3 minus x, and we see that that limit is 1, right? I can evaluate again with direct substitution. The left and right-sided limits then are different, okay? This means that the overall limit as x approaches 2, my function here, does not exist. Number 2 criteria is broken. So what I've got here is a function who's not continuous at x equals 2. Okay? I might be able to remove the discontinuity, but in general, this function is not continuous at 2. Right? So this video should give you kind of an overview of what it means to be continuous, what it means to have a function that's continuous at a specific value, looking a little bit closer at limits from the left and from the right, and then also the types of discontinuities and how we remove a discontinuity and what happens, when we can't remove a discontinuity, and then looking at some different classes of functions and being able to describe that they're continuous or not continuous, and an example or two. Thanks for watching.